Hi and welcome to video 7, unit 4, topic 5, and this is a video on confidence intervals for the Math Methods course. So you'll see our link here to the textbook work that we'll be covering here, and of course our success criteria and learning goals for you to read through and hopefully engage with. So confidence intervals are really the main feature of the whole topic here. Building confidence intervals is a really common statistical application of the work we've been doing really through the past 2.5 topics, through our binomial probability, normal probability, and also this situation, continuous, discrete variables, etc. You'll see confidence intervals come up as a statistical measure quite commonly. So the problem we've got is we've been dealing with a lot of examples where we know the value of p, and we're just playing around with, well, what could p hat be? What could the sample proportion be if we know the population proportion? Realistically though, if we have a large population, what you're actually going to do is take a sample and use the sample in order to try and get a better understanding of what the population proportion looks like. That's the goal here. So let's talk about how we could do that. The first thing we could do to determine the population proportion is take a sample, a single sample, assume it's a good representation of the population, and then just assume that the sample proportion equals the population proportion, and that the sample standard deviation, and that is our standard deviation calculation with p hat instead of p, well, just assume that that is equal to the population standard deviation, and that will give us a pretty good understanding. Now, of course, with a large sample, even out of a large population, this should be reasonable, but it won't be exact, or it's very unlikely to be exact. So we need to keep that in mind. We can do better. So let's consider some interval estimates. This just gives us a little bit more depth in our discussion about certainty and confidence in our result. So we've already established that for large sets of, or large n, large samples, the sample proportion is approximately normal. So of course we are dealing with these constraints. They are the ones that we've set up mathematically, but within different industries, different contexts, these may increase. There may be a higher expectation, a higher need for that normality to be strictly true. But generally speaking, if np is greater than 5 and n times q, or n times 1 minus p is greater than 5, it's going to be fairly approximate and a fairly good estimation. So that's our assumption based on this, and that's because we're dealing with situations where you take a sample and then you look at a common attribute and you count the number of things within that sample that have that common attribute. The number of people in the sample of 50 with blue eyes, or the number of math classes in a sample of 200 across the state that have more than 20 students, or something like that. There's always an attribute, so there's always a true false, and therefore it's binomial. So let's look at a single sample situation. Now what I've done here is I've identified, again I'm dealing with that idea of a known p. Let's say the population proportion, so that is just the expected value of the population, is the orange line. I've just drawn that orange line to show where it is. And I'll take a single sample, and you can see in my sample I've been a little bit radical, but in my sample, if that's the standard deviation, well then p is almost 2 standard deviations above the sample. Now if it's a reasonable sample for something that's reasonably normally approximated, well then this is an unlikely event, but I'm just using it as an example. If we take a we collect a sample of data and we model it using a normal distribution, and we gather our p hat, so our sample proportion, it should be a reasonable estimate of p, and this is one example of what could happen. It could be a bit under p. Let's have a look at some other options though. So we could have our bit under p there. Our dotted lines in all cases are sigma representations. Our second sample might be more compressed. We might have more or less variability in our data, a smaller standard deviation, but of course our mu in this case is larger than the actual p-value. Our third sample has moved back down. It's still more compressed than sample 1. It's a little bit more spread out than sample 2, but not much. But now the mean is back under. This one's pretty good. So we've got a mean there. Of course, we're not talking about the population standard deviation, so we don't know how spread out the population is, but you know that's a pretty good estimate. And sample 5 is way out. So we could get an example like this, sample 5, where we're just way off the charts, and that could happen. It's really unlikely. I'll put it there to show you it could happen. So you could collect multiple samples and get situations like this. The truth is that 68% of the samples you take will have P in here somewhere. So my data here is not really representative of what could really happen. So just be aware of that. That's what should happen ultimately. So now let's talk about confidence intervals. This is where we're heading. So here are some things we know. P, which is the population proportion, is also mu in our normal distribution. And sigma, as we've seen in previous lessons, can be calculated by doing the square root of P times 1 minus P over N. Now, we don't know P, but we do know N. And of course, so we don't know mu or sigma officially. That's our problem. But we have taken a sample, so we do know P hat. That's from our sample. So now let's say we're trying to find a value for the population proportion. What we do now is we flip everything that we've been doing over. We know the sample proportion, but we don't know the population proportion. Up here is an example of us using the sample to estimate the p-value. All of these little normal distributions are exactly that. Historically, you might look at, well, here's my p, and there's my normal distribution for p. I wonder where p hat ended up. Oh, I took a sample, p hat was there. I took another sample, p hat was there. I took another sample, p hat was there. And you start to think about, well, where did the sample data or sample statistic lie within the actual p, the population proportion value? But we've flipped this over and we're saying, where does the p-value lie compared to the sample statistics? That's the important feature here. We're flipping that consideration over. So let's do this down here. In the confidence intervals, we're going to think about it from the other side. Let's approximate P from our sample statistics. So let's swap out the P for P hat. So we're going to say now, well, we know P hat, so let's let mu be P hat, and sigma be all this stuff, but P hat's in there instead of P. And we're trying to find an approximate value of P. Now, this is all statistics, so we will never get the definite value of P unless we take a sample that's actually the whole population. So we do a census. But we can be approximate, and we can consider ways to be more approximate and use mathematics to build a good understanding of where P might lie. So let's say, for example, we want to consider when is, and this is not very good representation here. So we want to consider P is X when, what is the chance of P lying within one standard deviation of P hat? Where our standard deviation is also derived from P hat here. Now we know, again, from previous work that 68% of data will lie within one standard deviation. So what we could do here is we could say, well, the chance of P lying within one standard deviation is the probability that P is greater than or equal to negative Z, less than or equal to Z, where Z is 1. And then we could look at Z and say, well, what do we know? What do we know about Z here? We know that Z is equal to X minus mu over sigma. We have a value for mu, we have a value for sigma, and we have a value for X because X is the thing we're trying to approximate. So we put in our X, which is P, we put in our mu, which is P hat, and we put in our sigma. This has all come from up here. These are the values that we know once we did that P hat P swap. So now I go, well, the probability that Z is between -1 and 1 is 0.68. It's actually 0.68, I think 26 or something like that. But anyway, we're rounding here and we're using that 68, 95, 99.7 rule. And so we swap Z out and we put what Z is equal to. And now I'm going to do a little bit of maths here, or I've already done a little bit of maths. You can play around with this, but I've rearranged it. And what we're actually determining is the probability that P is between two given values, which I'll show you a calculation of later, is equal to 68%. And this is called a confidence interval. It will come out with something like this. The probability that P is between, I don't know, negative is not very good usually, 11, P, and 15 is equal to 68%. And that's a really important statistic So that then you can present, or you can use, and you can say, I'm confident, pretty confident, that P is between 11 and 15. Now, to be honest, 68% is not commonly used for confidence intervals because, yeah, it's better than half, but it's not that great. So we actually usually go a little bit further. So 68% in this case was my example I wanted to build up with, but actually more commonly we're using 90%, 95% or 99%. And again, it depends on what we're trying to find. If we're just doing some statistical measures on some basic community values or maybe some school data, 90% might be fine. If we're doing some statistical measures about the stress and weight carrying capabilities of certain steel structures that we're going to use to engineer a bridge, we might want to be a little bit more confident about that. So we might take this a little bit further. But the principle is still the same. For a 68% confidence interval, we use the Z-score of 1. For a 90% confidence interval, the Z-score has to be 1.64. Now, 95 is one of those special ones. It doesn't actually equal 2, though. It equals 1.96. It's pretty close to 2. And 99% is 2.58. These are the ones that we will use all the time. So, you could remember those numbers. In your external exam, there's a good chance one of those will come up. Probably 95. It seems to be the most common, but I can't predict that. The other thing you can do, though, is not remember those numbers and just remember that you can go into your calculator and inverse norm that question. So we want to find the center of our distribution to have either 90% of the data or 95% of the data or 99% of the data or any other value. And we're trying to calculate the Z-score that will work for that. We've got a mu of 0 and a sigma of sigma of 1 and a mu of 0, and our Z-score is these values just here, one of those values, and it will give us the particular Z-score that will work, the Z value that